Hello guys, I just thought I'd just do a video about this type of soldering iron. I quite like it. I got it, and basically it's taken over the old stuff where you just used to heat it up. So I thought I'd do a script again because I just can't remember anything. So yeah, so hand soldering guide, tips, flux, rail world. Right, it's just my personal view on things. It's not a professional thing. It's not an exact science. It's just the way I do things, and it's just my view. So just take it all with a pinch of salt. You know, it's just my personal take on soldering. I'm just a hobbyist. I just build projects. And like I say, other people have their own methods, their own preferences, and their own reasons for doing things differently. It's theory and practice just aren't the same thing. So I just hope any of this will help you, or maybe just improve the way you do things, or see things from my point of view. I don't know. So I'm going to talk about our soldering tips, the modern ones. Right, so we've come from these. Where's my there? So these old ones, we've got a big heater inside here. It's just a big corner wire. It just glows red hot and heats the thing up. And inside, basically, we've just got a big chunk of copper, and it just heats the copper. But the thing is, with these old tips, I don't know if we can get this zoomed in there. Let's see if I can get that focused. You see the end of the tip there, it's basically it gets eaten away. So what you do is you keep cleaning it, and then it'd eat away, and then you clean it up again, reshape it. And that's what solder does to copper. It dissolves it. Believe it or not, solder dissolves copper. So anyways, well, with heat applied, of course. So the modern tip is completely different, like this one. Now the modern tip we'll just talk about this end bit here. So you know, I mean, there's different tips with different connections for different models. You know, you buy our soldering iron, you have to use our tips, sort of thing. You know, manufacturers aren't going to decide and make them all exactly the same, are they? So yeah, so what I'll do is I'll just talk about from this point onwards up to the tip. I'm just going to bring a drawing up. Let me just get that. Yeah, right. So how modern soldering tips are built. Soldering tips used to be just a simple copper rod, like I've just shown you, and they work, but they dissolve in solder, oxidize quickly, and don't hold temperature. Modern tips are engineered structures. Right, so they have a copper core, which is is the best sort of thing for thermal conductivity, and it has an iron plating. And the reason for that is solder wets on iron, but it doesn't dissolve it, and so it's going to last longer. So if you ever looked at a tip, so I've drawn this tip, you'll notice that the end looks a bit different from the stuff. Basically, this outer coating is chromed. It's copper. It's iron chromed. What I've done is I've broken this down into pieces, but the bit at the end, you'll notice that solders is actually iron. It's a copper coated with iron at the end. So you've got copper underneath the iron, but which conducts the heat. But because it's got an iron coating, then the solder doesn't melt away the copper. Right, what I've done here is I've actually done a section through this tip. So what I'll do is I'll just get rid of that one. Actually what I'll do is I think I will do a section through the whole thing so you can actually see it to start with. Let me just do I'm just going to think about this. Yeah, there's a couple on FreeCAD and I usually end up getting the wrong one. But yes, so what I've done is I've clipped through the thing so you can see where the rings are here. The wires come in and they just go down. What we have is a thin piece of stainless here for so it conducts less heat. It acts like a throttle for heat to travel, and then that is inside this thin tube at the end. That is just a thin tube of stainless. Stainless can take heat really well, and because it's so thin, it's also strong with it being thin. Because it's so thin, it doesn't let so much heat travel down into the handle, but keeps all the heat up towards the end here. And what we have is we have a heater element, a thermocouple, we have the copper core, and then we have the iron core. So what I'll do is there's a better view of this, I'll just change the view. There we go, I've done this view so it looks a lot better. It doesn't have the hollow bits. But this is the actual tip. So what we have is we have our heating element. The two wires are coming down from the two rings that plug in at the end. They come down to this heating element which heats up, and it heats up this solid copper core basically. So you've got a nice piece of copper here, but as I mentioned before, copper oxidizes and deteriorates with heat, so you've got this big heating element heating this lump of copper. So what they do is with this lump of copper in the middle is they coat the inside with nickel. So you have like a nickel coating on the inside. This stops the copper core from oxidizing from the heat of this heater element. This is our thermocouple, which is used to get the temperature at this point. It's kept as close to the end of the tip as possible, but we still need a big lump of copper here, so it's not actually taking a temperature at this tip. It's taking a temperature around this area here basically, well, where it is. And if you know that when you heat something up, as it radiates, it cools down, so that you're gonna, because the heating element is down here, this temperature that you are reading on your either station or your actual where are we? Or actual readout on your thing there is actually going to be hotter than what the actual tip is. So what you have to remember is the shape of your tip. I tend to use this conical type with quite a sharp point, and this tip is actually a lot colder than it is here at this end here, because we are reducing the cross-sectional area of the copper, and as we reduce the copper cross-section of the copper, we are actually reducing the we're sort of like throttling the heat that actually can travel down it. So we need to actually raise the temperature here to get a reasonable temperature here. Yeah, so you depending on your type of tip you have, you may want to have your soldering iron set at different temperatures because of the way it transfers heat from this area down to this area. If you've only got a small point, then you're going to actually have to have more heat to get it to travel down to the tip. Right, so we've got the copper core, and then this copper core is actually coated in an iron casing. So we actually cover the copper here with iron. We've got the main core here transferring heat, but a lot of it is iron as well, because iron's a bit cheaper than copper. But we need the iron because we don't want the copper core to oxidize. So basically they wrap it in iron, and we get iron all the way down to the tip. And then after the iron, we then have, on top of the iron is, we have it's chromed. We have it's sort of like a nickel or chromium coating around the iron, and that stops the iron from oxidizing. Basically it stops it rusting. That's what rust is oxidization. So it stops the iron from oxidizing. But what we don't want is the chrome right to the tip, and so what we do, the chrome stops about here, and it leaves the iron open to the solder, and solder will actually wet onto iron really easy, but the solder doesn't eat iron, so the tip doesn't get eaten away. And so this end bit here, basically you need to keep it tinned so that we don't get any oxidization of the iron to make it go rusty. Because if it goes rusty, the iron end here, and you break through to the copper, then basically your tip is going to go just disintegrate, basically, because your tip will start eating away from the inside here. So as long as you keep that tinned, that's going to be okay. They should actually come from the manufacturer already pre-tinned, so they don't oxidize. Yeah, so that's the modern tip. I hope you found that quite interesting. What I'm going to do next is, while we're on this page, let's just have a look at my notes. So I've gone over the copper core, iron plating, nickel barrier, chromium outer plating prevents rust and stops solder wetting, and the exposed iron at the very tip is the only place solder should wet. So basically that's why they have that tip. Let's have a closer look and see if I can get that zoomed in. Where are we? Is that going to focus for us? No, is it? Bollocks. Come on, focus. Focus. Come on. It's not going to do it for us, is it? There, twat. Wonder if I click on there, will that help? Oh, there we go. Yeah, I should have used my mouse. Right, so there we go. So you can see where get it in focus again. You can see, well, this is the stainless steel sleeve, so this just stains like stainless. You get the rainbow effect from heat. And then where the tip is here, this mucky brown bit where the burnt flux is, that there is chromium, so the actual solder doesn't stick to the chromium. And then you've got the end bit, the tip there, which is actually the exposed iron that's wrapped around the copper core, which is tinned. So there we go. Yeah, what I want to do is actually next is some people these soldering irons you can actually put your own logo on, and you can upgrade the firmware. So I'm going to do that. Let's just have a check my notes. Yeah, keep the surface tinned, and what's next? Inside the temperature sensor. Yeah, so we've got a heating coil wrapped close to the working area. Thermal couple. They generate a tiny voltage, and then the station amplifies this through an op-amp, and the temperature is only measured when the heater is off, because you can't measure those tiny voltages while you're sticking a big chunk of voltage in there. So yeah, heat measure, that's how it works, and that's how it manages it to keep it at that steady temperature. So, tip damage, yeah. So why temperature matters: high temperatures accelerate iron plating erosion, chrome flaking, oxidation of the working surface. So once it starts, it stops weighing. People turn the temperature up, think even more, which makes the problem even worse. So hand soldering, you want to be between sort of like 300 and 350 is a great working range. Over 400 plus, it shortens the tip life. Once the iron layer is breached, the copper core dissolves like sugar in tea. There we go. Solder types. Right, so before we're going to go to solder types, right, what I say, there's only three really matter. There's three solder types, and I'm going to go into that and explain why I say there's only, there's hundreds out there on the market, but what you need to look at is just three types really, and then each of the three types have various little bits added and stuff. But I suppose you could sort of call it three families. I don't know. Anyway, see. But first of all, what I'm going to do is talk about upgrading this the soldering iron. It's a TS101, I think, if I remember right. Can we focus? Come on. There we go. Can you just see it? Yeah, TS101. That's what I've got. And so what I'll do is I'll just plug it in. And as we plug it in, you need to watch the screen, and it should give you the version, and it should have my little logo. Let's try it. Hang on, try it. Yes. Oh, right. We're out of focus. Right. There we go. It's back in focus. Try again. There. You see my little logo? It didn't stay up long. You'd think they'd make it last a little bit longer, but it's there anyway. One more time. Right. So, yeah, and it's version 2.11. Yes, so right, to update this, we're not going to use the power lead. We're going to actually use a data lead. So what I have here is a data lead. Where are we? There we go. Let's try and focus about here somewhere. Come on, there we go. Yeah. So what we have is a data lead. When you plug a data lead in, right, first thing it happens is comes on, and what will happen is on your computer it will show up as a drive, TS100 app D, and we've got our logo bitmap, and we've got configuring text. What's that? Yeah. So what you can do is you know when you go into your let's bring them over here. When you go into your settings, you can press your buttons. If you follow the manual, go into settings and change all your different settings, and you've got about 18 different settings that you can change. Well, if you want to not bother going through click and on the thing, you can actually use this configuring text, and you can actually set all the settings here. So that the hash there is a comment, but the actual value is this one here, where you've got an equals 3 backlight, and so idle temperature is 240. That's what all the settings are, and you can actually just type them in here and save the text in this this folder. And if you want to do a backup, you can also save that text somewhere else on your PC as well. And then if you ever mess up or do something to mess some settings up, you've got your backup on your PC, you can then just copy it back into this file, because this D is actually a virtual drive on this actual soldering iron. And the logo, right, so that's my logo. What we have, if I go to view by large icons, you can see there. So let's just open that and zoom in. There, you can see that's what my logo is. Now this has to be a special format. It has to be 128 by 32 bits, and it has to be 1-bit depth color resolution. Basically black and white is so 1 bit. Now what you may find is you've made it the right size and you've made it black and white, but when you've saved it as a bitmap, you haven't actually saved it as a 1-bit color depth file. If we can just check this by, in fact, we go properties on this, and we just bring up the properties and go to details. You can see the bit depth is 1 here. Now if that's a bigger number than 1, it won't work. So let me just cancel that. Now what I have actually, and what I use, I've got it on, I've published it on the Microsoft Store website. So you got a Microsoft Store website, and it is this little editor program I've got. This is a little pixel editor. There we go. So if we look full width, and we can see that it is the width is 128 and the height is 32, and you can you can use this to edit this little bitmap. And so if I went with, say, white, we can put like a nice little star here, something like that. We can zoom in, do it even better. If you zoom right in, it'll show you all the pixels, and so we can make this a lot better. Let's see, let's go like that. Yeah, make it a really bit bigger. Go back, go with black again there. So we like 4 from 2 from that way. That's full height. There we go. So we got 1. Now let's go down to about there. I'm going to get the white. Go down to about there. Damn, I went too far. So I've left 3. So 1, 2, 3, about there then. So let's go with that. Get them in black back. Yep, there we go. And let's go with the middle bit, white. Let's get that. So what have we got there? It's about middle there, isn't it? I went 3 thick, didn't I? Let's get that. And edit that a bit longer. Still looks a bit offset. Got that about right? Yeah. And then so let's sort of, it doesn't look quite right, does it? Maybe one there. Yeah, that looks better, doesn't it? There we go. Yeah, let's try and match that. Yeah. Zoom in a bit. Zoom in a bit better. There we go. Yeah, let's just get some more white in there. My hand's all over with the mouse. I think I need it. Oh, I'm really messing it up. I might do better when I with black. Right, so we're down to about there, and we can go up 1, 2, 3. Yeah, there we go. And so that wants to be about, is that level, or are we on with that one there? I think that one. No, I went too far, didn't I? something like close. Getting closer. One there, one there, one there. And do I need one here and there? Oh no, it was there, wasn't it? Oh, was it? No, I think that there is. Oh right, that one there. So right, let's get that off there. Then it goes like that. That's more like it. There we go. We just got to get these two sides to sort of look similar. Get in there. Does that look right? Oh, I think go down. No, we need another one. We need to go one more level. Let's go like that. There. Let's get me black again. So that wants to be white, that wants to be black. So let's get rid of all them. I want that one. Do I? Oh, hang about. No, it goes like that. No, that's wrong again. White starts there, there, and that's there. Why does that look odd? 1, 2, 3, 4. 1, 2, 3. That wants to be black. That wants to be white. There, that looks. There we go. That looks it. Right, so we'll leave that like that. Okay, so with my little application, we need to save this as a BMP bitmap. But we need to save it as a 1-bit resolution. So I've got this checkbox here. So we need to make sure that's checked. And what we'll do is I'll resave this. They look a bit long, don't they? But anyways, you'll see what I mean. You saw my little thing boot up with the original, and now we've got this little star at the end. So we've got to save ours. And what we need to do is we need to save it in here where we save the logo. If we just go view large icons, so we can see that's the original one. We're going to right over the top of that one, and so we're going to go save. Yes. And so what we should now have is the new one. This is actually in the soldering iron. I mean, you could have made this and saved it somewhere else on your computer, then copied it across to this folder once you've plugged the soldering iron in. So let's just minimize that. We don't need to look at the settings anymore. That was pretty straightforward, wasn't it? But what I'll do is I will unplug and plug that back in again. So let's just do that. Oh, this is going to disappear anyway, so I might as well close that. And so we're sort of let's zoom, let's get focused. There, that's did a good job that time. So I'll unplug it and we'll plug it back in, and there you can see the new logo that we've just edited. So yeah, my little app is on is on Microsoft Store. So yeah, I've got some links on my main web page. Hang on, where's my main web page? Let me just bring that in. Where is it? Yeah, if you go to my main web page, I've got there this link to Microsoft Store. Just go there, and it's this one here, this small screen pixel editor. I'm just updating at the moment, so you need the version that has. Let me see. Let me just open it up again. There we go. Pixel editor. You need the version that has make bitmap BMP 1-bit so you can tick it basically when you save the thing, and you save it. Make sure the image is actually 128 by 32 pixels. If you're going to do a new one, all you have to on my application is you just need to type in 128 here, 64 there, and just click new. That'll give you a new one to start doing all your editing on. It gives you a fresh blank thing. Actually, I've got 64 there, that should be 32. Let's try again. New. There we go. We've got a new one, and basically it's up to you whether you have a white background or a black background, but do whichever you want. Okay, close that. Right, so that is that done. So that's when you that's by just literally just plugging a data lead in there. Now to update the firmware, that's a different procedure, and it's not as simple. Right, well, it is simple, but it depends whether you have a Windows 11 machine or a Windows 10 machine. If you've got a Windows 10 machine, you're fine. There's going to be no issues. If you've got a Windows 11, what we'll do is we'll unplug the data. Right, you have to put it into the update mode, which is by holding this button A. So you hold the button A and you plug in. This time it brings up the DFU. Now if we click on there, we can see the DFU is version 1.05. This is old. It's got an old chip in here. Well, I reckon that they all have old chips in there, but you know, I say old chip. There's nothing wrong with the chips. The chips are brilliant, and the microcontrollers are great. It's just that USB has moved on. We're now on USB 3. I think when this chip was designed, it'll have been USB 2 only. And so Windows 11 basically runs too fast for these chips. So the idea is, what you do is, once you've got it into this mode, basically you hold this button A down while you plug the data lead in, and now it opens up a different drive. Like I said, it opens up the DFU drive, and this is for upgrading. Now you may not see these files here because these are hidden, and I've got my settings so that I can see hidden files. So when you do it and you've got the DFU here and the DFU there, but you see nothing in there, don't worry about it. It's probably because your settings don't allow you to see hidden files, and these files are hidden files. So once you've done that, you've plugged in there, basically what you do is you go to their website. So this is their website. Well, actually, this is the website for my soldering iron. Obviously, yours will have a different website if it's a different make, but I'm sure it will be very similar and done the same way. Basically, you upgrade firmware on these things the same way, no matter what. Anyways, it's all done the same way. So for mine, I went to this address, eDesign, which is Miniware. So it's the TS101 Smart Soldering Iron, and obviously you can see it's been the firmware has been updated from 1.11 up to 2, 2.1, 2.06, 2.10, and 2.11. So basically you just click this link, download it and save it. You can get the latest user manual, although it won't show you what I'm doing now. Well, sort of. So yeah, you download it. So basically that's where you download the stuff from. Once you've got all that information, you end up with, let me just find, I don't need that, find the file. Here we go. So yes, so there's the version 2, is the version 2.11. So I've unzipped it, and you can see that you've got this hex file here. This is the hex file you want. If you've got a different language, then you've got these other hex files that you can add after this one. So you add this one first, and then you add the others. If you want a Chinese, don't know what's that, is that Dutch and this Russian? But anyways, those are the choices you've got. You've got README, that'll tell you actually what to do. So there you go, how to upgrade. Is basically what I'm going to do is just hold the button while you plug in your data lead, and then what you do is you copy this across. Now what should happen, now I'm on Windows 11 and this is not going to work. This is what you should do, is you grab that and you just copy it across to the drive on that, your virtual drive of your soldering iron, and you just drop it in. It copies across, it goes ping 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 and opens again, but you can see that mine says error. This is because it didn't copy correctly. Basically Windows 11 is too fast for this virtual drive. Windows is too fast for this virtual drive on the microcontroller. So but Windows 10 uses different USB drivers, and it's slower than Windows 11. So what happens is when you copy it across, it'll say ready instead of error. I will show you this in a moment, because what I'll do is I'll start up a virtual Windows 10. Yes, this is error, and then once you've the files copied across, all you do then is you unplug the thing again, and then you just plug it back in, and then what it should do is come up with the new version on there. It'll come up with the USB drive, but this isn't the same drive this time. This is the where you can just stick files and stuff. So what we'll do is I'm going to do this again, but I'm just going to set up Windows 10. Okay, so I'll close that. Right, okay, so I've used VMware, anything that will run a virtual machine basically, and what I've got is Windows 10 here. So what we can do is now I'll just unplug that. Right, so okay. What you need to do is obviously when you run your virtual machine, if you have Windows 11 and you want to upgrade your soldering iron, and you create a Windows 10 machine on your soldering, you need to copy the files, the hex files from that folder that we had, across onto the virtual machine drive, so we can get to them. So there's the version TS101 app v2.11 hex. So this is the one, well, it's already on here, but I'll run through it again. So this time what we do, as before, you hold the button A because we're going into the firmware update. Hold that in and then plug in your USB, like so. It's asking me which machine we want to connect to the virtual machine, so go OK, and there we are. We have the same virtual folder now that we had before on my Windows 11, but now we're actually in the Windows 10 virtual machine. So Windows 10 works fine. It's got a different USB way of speaking. Actually, it's slower, it's less picky, if you know what I mean. So you just copy your file again, drag it across, but this time it should look different. So I'll just drag this across and copy it into the virtual drive on this soldering iron. And what it'll do, it'll copy the file across this time, and you can see there, and it goes ping ping ping, and this time when the virtual drive reopens, it says RDY. That means it's ready. It has worked. Basically what it's done is we've copied this across, and it's now ready to and it's basically decompiled the X file, and it's ready to swap over to the new version. And to do that, all you have to do is just unplug your soldering iron, and then you just plug it back in again. This time it'll try to open up the it'll open up just the normal virtual folder, but you'll have seen that it has the new firmware when it boots. So let's just I can close this now. So you've seen it work, and you've seen it, you know, pressing this button and what have you. So if you've got Windows 10, you're going to have no problem. Windows 11, you're going to have a problem. So let's just suspend that. Yeah, why not? Really confuse it when it reopens. So basically, oh, that's just the file reopening. Now I've closed my virtual. So we're back on Windows 11. I don't need to look in there, but it's going to pop up again once I do the plugin. So this time, like I say, when you plug in the just zoom in there, when you plug in the after the new update, you know, when it's said ready, you plug it back in, and you should see the new version displayed on the yeah, and if that didn't pop up in front of it. Right, so we try that again. Right, I'll just move that to my other window. Right, so there we go. Plug the USB in. There we go, and there you go, version 2.11. Okay, so that has been updated. I'm not going to use the data cable for actually running the USB thing. I don't think it can supply enough power. That what does it do? Does it do anything? Does it tell you? Oh, there, so it says low volts. Look, yeah, because this is my data cable. So we now bring back the actual power cable. This is into my USB power supply, which has got 100 watts. And basically, as soon as I click that, that'll heat up. But we're not going to do that just yet. Just give me a moment. Alright, so this is my view on things. Basically, solder types, only three really matter. We've got lead free with silver and copper alloys. We've got the 64 tin lead, and we've got the 6337 tin lead, and it's, well, Eutectic, that's how you pronounce it, Eutectic. This is very special, this Eutectic, and it gives this 6337 special properties, magic. But I wouldn't recommend using 6337 for general use. Well, it has its pros and it has its cons. I would use 6337 in controlled environments, like in reflow ovens and hot plates and things like that. Because Eutectic, well, let's go in. I'll carry on. So most of the variants are just tiny tweaks, a bit of silver here and a bit of copper there, or different flux cores, and basically a lot of people use this an external flux, you know, a syringe or whatever full of flux anyways. So basically these three, it's the lead content really, and copper and silver that matter. So we can ignore the flux for the moment, because if you're using an external flux, and if some people do, because basically well, they're doing things wrong. You shouldn't need a lot of flux. The flux is in, if you've got flux cord solder, the flux is in your solder, so you've got plenty of flux there. The trouble is people just burn the flux away, and that's why they have to keep adding more, because they've actually just disintegrated the flux from the iron being too hot. What have I said? Flux misuse. Yeah, why people add too much flux. Right, so this is an important value here. You see this degree here, 80 to 20. This is the range the flux should be working in. It shouldn't be working any well, it doesn't work when it's colder, and it shouldn't be working when it's any hotter either. You shouldn't have it hotter than that for the flux to work. For the flux is a chemical reaction. It's not magic. It doesn't sort of do stuff. It does something when it gets to a certain temperature, and that's the temperature range that the flux works in. It cleans, oxidizes, and allows solder to wet the metal. Cleans oxides. It gets rid of the oxide, so the solder can actually wet the metal. When we say wet the metal, it means the solder can actually merge with the metal, basically. And flux is destroyed over 300 degrees C. So if you heat flux up to over 300 degrees C, you've destroyed it. It no longer works, and that's why people tend to add more flux, because they've just killed the stuff they had already. So if you're going to heat the flux up above 300 degrees, I mean flux. Well, I'm really talking about what do you call it? Rosin. Actually, rosin is a is organic, and I know most organic stuff is carbon based, and I know from past history when I used to try and crack oil, which is carbon, I used to try and crack oil, engine oil down to shorter strings of carbon. You had to take it above 300 degrees, because that's how you sort of evaporated it, and you sort of dropped it. So anything organic, you take above 300 degrees, it just gets carbonized, basically. So yeah. So if your iron is too hot, the flux burns instantly, and you see smoke. The joint goes dull. You think you need more flux, but the real issue is the temperature. Flux isn't flux isn't magic. It's chemistry with temperature windows. Stay in the window, and you barely need any. So you hardly need any if you just stay within this temperature here. And like I say, well, when we later look at the melting temperatures of solder, you'll find that the solder melts it within these temperatures also. So although now, don't get me wrong, as I said before, when you have something like this, like where are we? This in focus, your temperature is reading a temperature about this point. Let me just get a pointing stick. Yeah, your temperature is reading a temperature in here. In here, your thermocouple is here, right next to the heating element inside there. So this is the temperature you're seeing that's been displayed on the screen. When it displays it on the screen, it's the temperature here. Where are we? It's the temperature here that you're actually seeing, or just here. This is where about the thermocouple is. But you can see this tip narrows down really quickly, and so the temperature over here is going to be a lot less than it is back here. So you tend to up your temperature on your soldering iron to get the right temperature that you want here. And this will vary, because if we take a look at two other tips, I'll give two other examples. Like I say, this is the one that I use, this type. Where are we? That type. And I run about 300 degrees on my soldering iron. I run it at 300 degrees. Let's just put it up. There we go. If I go up, it goes fairly quickly, but it goes up to I have it set at 300. Well, you can see my T1 setting there, 300 degrees. So we go to 300 degrees. But like I say, the 300 degrees is at the point here where the heating element is. It's not at the tip. A good thing to do, let me just turn it off. I'll just move that out of the way to cool down now. If we look at the other tips, two other examples, can you see that this knife one? Now we're going to have quite a high temperature here, but can you see how thin it is? It gets really thin here, and we've got a really long, thin tip. This one will have to be even higher here to get a temperature that we want here at this tip. But if we take a look at this one, the favourites of most, can you see how big and hefty this block is here? The main core here. The temperature here is going. It's because it's really thick and heavy. The temperature is actually going to move down here really easy, and so it will actually heat this up a lot easier than it did the other two types of soldering iron, because it's a nice big thick block of copper, and it can conduct a lot of heat quickly and across to this tip. So you're going to find that this one actually works better than the other two. But the fact is that you just need to up the temperature a bit, so that the loss you get from going through this thin bit of copper to the tip is compensated for. Now what I tend to do is I have a multimeter with a thermal couple you can stick on there. And what I do is I check the difference between this temperature here and that temperature there. So you can see, what you can find out is how much lower the temperature is here than it is there. And then you know how much higher to set your temperature. And you'll find it's different for this one. On this one, this will be a lot colder than on the tip than this one, because you can see that the different thicknesses of the tip. And that's what you've got to consider. And once you know them, basically you'll end up with maybe 3 different tips that you use, like this knife one, this flat-footed one, and I use this pointy one. This one usually needs to be up higher. But what you'll have on my tool is I have 3 settings. I have, oh, hang on, wrong thing. Oh, shit! Pressed the wrong button. I have 3 presets basically. Hang on, wait till it boots up. I have to turn it back on again now. There, I have three presets. So I can have that one, I can have 330, and I can have 350, and back to 300 again, depending on which tip that's in the end of my soldering iron. Right, so we've got that done. What I'll do is I will change to this one, because it'll be able to show the 3 different solders easier. So let me just find my pliers. I'll be right back. Alright, so let's get back. So yeah, flux you don't want to be burning it, basically. That's it. And like I say, you've got to take into account different, the tip of your soldering iron isn't actually the temperature you read on the actual iron itself, depending on the type of tip you've got. So the tip is actually going to be into this range, even though that I run my soldering iron at 300. At the tip it'll probably be within this range here. So flux, burn, smoke, done that, haven't we? Exceed the amount of flux. I mean, what people tend to do is add flux, and what they're actually doing is cooling their tip down, so the flux actually works. I don't know if I've mentioned that here, did I? Yeah. Right. No, I didn't. Right. So somebody will be putting their soldering iron on the thing, and they think, I need more flux, and so they add more flux. But the reason the flux actually works is because it actually cools the tip of the soldering iron down to the working temperature it can work at, and that's why it seems to work. So, alloy behaviour theory versus real world practice. Melting points of pure metals. Right, so tin, it melts at 232. Lead melts at 327. And copper melts at 1085 degrees C. And you think, right, you can scream at the screen now, because you can say, well, my solder melts at a lower temperature than this. And yes, it does. Even though it's made of lead and tin, it melts at a lower temperature than what tin and lead melt at. And this is a very this is a process. This is what happens when you create alloys, and the reason why we mix lead and tin at certain percentages, because mixing at certain percentages alters the chemistry of the alloy. It alters the crystalline structure, and it enables them to melt at a lower temperature, believe it or not. So when you mix, it can drop. When you mix metals, the melting point can drop dramatically. Alloys disrupt the crystal structure, making it easy for the solid to transition into a liquid. So basically, that's. Adding copper changes was that silver and copper? Don't know what that SN is. That silver and copper alloys melt higher. So the lead-free and silver and copper shift the melting point. So we now have lead-free, and personally I use lead-free. Because it makes no difference. It's your own preference. People say use lead and tin because it melts at a lower melting point, but no. Yes, it does, but no. What you have to remember is what they should be saying is use 60-40 instead of 63-70. 73. No, 63-37. You should. I'll come to that in a minute. Well, I've got a table somewhere. Right. 63-37 tin lead is eutectic alloy. Right. What this means is it melts at 183 degrees. There's no plastic phase. It turns instantly from a solid to a liquid. It either is liquid or it is solid. It's one or the other. There's no in between, and that's what 63-37 tin lead solder is for. It's what I call it's. I would say it's best used in controlled conditions. So you can control in temperatures, like in a reflow oven or on a hot plate. You're controlling the temperature precisely, and you can go bring the temperature up just above 183 degrees. It melts, and then you just drop the temperature down below 183, and it's solid again. That's it. So it's just a type of lead that's used in factories where it goes through on a conveyor belt, goes through an oven, and it goes through a heating process. But you know that when it hits 183 it's liquid, and then when it drops below 183 it's actually solid. It just half a degree below 183 it's solid. Half a degree above 183 it's liquid. That's what it does. It's a bit, I don't know if you've seen them YouTubes about dry ice and stuff. It goes from gas to solid, but it's a similar thing. It's eutectic. Anyway, that's the theory anyway. So, but in DIY it doesn't always match the practice. Yes, components heat unevenly, pads heat at different rates, thermal mass varies. You don't have control over a heating curve. That's what I'm saying. Is you don't when you're doing it by hand in practice, you want something that gives a little, if you know what I mean. If it's close enough to that temperature, it should still be runny. If whatever. So hot plates, preheater setups and stuff. It matters, but you have to remember that what the solder does when you're using it, basically, and you expect if you know that if you know what 6337 tin lead does, where it actually it's either one or the other, then using it is a lot easier to use, basically. So you know what's going to happen. And so here we go. What have I got here? Do I need to make that bigger? Oops. Yeah. So so if we look at 37, so you've got tin, it melts at that, and you've got lead melting at that. But when you mix them both together, it drops the point at which it actually melts. And this is just a single point, so like I said, it's either solid or it's liquid, either side of this 183. Whereas 6040, we've got the same conditions, the tin and lead it melt at higher temperatures, but we've got the 183 to 190, so it will be runny in between them. It'll be sort of like a hot jam sort of scenario where it sort of melts. Well, it's a bit like chocolate, really. When you warm chocolate, it gets soft, doesn't it, and then it becomes runny. So you've got a range of temperature, and so you can manage to play with this better. This I would recommend using the 6040 when you do the trick, where when you've got like a surface mount component and it's got lots of legs on it, and basically you just bridge all the legs together so you can heat them all up with a big blob of solder. Well, you don't want to be using the 6337 in that point. You want to be using the 6040 lead, which melts a lower temperature. But then I use lead free. Now lead free has the same sort of properties as the 6040, except it's just at a bit higher temperature. And since people don't have their soldering irons at a very high temperature, it'll melt. The soldering iron is going to melt either one, no matter what. I mean, if you've got your soldering iron set higher than 220 degrees C, then it doesn't really matter whether you use leaded or you use unleaded. They're both going to melt. I mean, they've got no choice but to melt if you're above 220 degrees. I don't see the issue of turning to this lead, but actually this is easier for removing surface mounted pieces. But you don't want to be using the 6337. 6337 is well, like I said, you'll think you've got the chip sort of loose and everything, and then you go to lift it and it's rock solid again because it's just dropped below 183. Whereas with 6040 you can warm it up a little higher, say up to 190, and you're still within, where are we? We're still within the flux activate where the flux activates, so we're still within this 180 to 220. Which is what this range is in, sort of thing. So either case, I don't see the difference. But you want to, for doing that trick, you want to stay away from the 6337. Anyway, let's just demonstrate these. See if I can try and demonstrate that hot, that's solid, and it isn't. So I've got 3 blobs of solder here. I've got me what was that there? My 6040. Yeah, there's my bit of 6040. I only use it when needed. There's my 6337. Use that when absolutely needed. And there is my lead free, which I use all the time, basically. Actually, this is a bit on the thick side, is this? But the thing is, I got a 500 gram roll of it for just 15 quid. So I couldn't sort of refuse that offer. I would have. It should have been about 50 quid, really. Yeah. So let's turn my soldering iron on. Ping like that. That should heat the thing up to 300. Now, normally, what I would recommend is, if you're doing a big sort of like with a big ground plane as well, everything, is I would warm this up. I would warm it up to about maybe 150, something like that, and basically it'll stop the everything in the universe wants to be the same temperature. Once you understand that everything wants to be the same temperature, you'll know how things work. So if this is colder, it's going to take the heat out of the iron to get to that temperature of the iron, and so basically, what you mix something cold with something hot. Basically, they want to be the same temperature. The iron will try and cool down to be as cold as what you're touching, and whatever you're touching will try to heat up to be whatever's hotter. So it's just thermodynamics, really. Everything wants to be the same temperature. But if you're going to heat up a big area, it's going to take a while for your soldering iron to heat up the whole area. So you're best off preheating it. I'm just going to just dump this on top of that. The middle bit is my 63. So let's just stick that in there. Let's just warm the whole thing up. Just for now. I've got a boost on this. I can boost it up actually and put some heat into this plate. So I will do that. Right, so what I want to do, try and show this, might be better off with a knife. Right, so if I poke this with a knife, it's solid here. I'll tell you what, let's just I don't know what view I've got that on. I don't know if I've got it zoomed in. Have I got it zoomed in? Telephoto. Yeah, there we go. New camera my son bought me. Well, gave me. He bought a new one. Where are we? There we go. Get it in the middle. Right, yeah, so I can just poke with my thing, because what I want to show you is when you're actually using 6337, you might warm an area up, like here, and you can see that round my soldering iron it is soft, but this area is still cold and it's solid as a rock. Can you see? It's still rock. to get the whole thing melted, you've got to heat up the whole solder and keep heating up the whole solder. As soon as you move away from that, this here is going to go solid because it's dropped, whereas this is still liquid here, but at this side it's rock solid. Whereas with I think this is my 6040, if we just heat this up, I can just leave it in where it is, and it's actually melted the whole area. The solder all around it is soft. So using 6040 is the thing to use when you're sort of like doing a large area of solder where you're trying to get some component off. I don't know, have I got a component here throwing around? I think I binned them all. But you know where you've got something. Well, I better just grab that with tweezers. But you've got something with 4 legs on, and you want to solder all 4 legs. Let's get that a little better. Ooh. You want to solder all 4 legs. You can heat up the whole solder on the 4 legs, and this is the 6040. So the 6040 is just trying to get a better grip of that. Yeah, bring in the heavy artillery. There we go. Grip with that now. So now I can just sort of heat up the solder, and the whole thing comes off because the whole solder, it's got a bigger range of melting point basically, and it's a lot easier to get all the pins off. Whereas if we go to the 3763, this I've got to go over to this pin, heat that up, and as soon as I go to this pin here, that one there is now solid, so I can warm it up here, and that one's solid, and I've got to go back and keep heating the whole area up to get that off. Whereas with this I just had to do just the solder, and it's done. I hope I sort of explained that. And of course the lead free is just as easy to use. In fact, I prefer lead free to the actual 6040. That can you see how that is all totally runny, even though that my soldering iron isn't over there. It just pulls the whole thing up. The range of heat at which it melts is greater, but your 6337 it's either solid or it's liquid. It's one or the other. That's still solid there, and that is liquid. Anyway, I hope that made some sort of sense. I'm probably talking a lot of bullshit, but anyways, it's the way I see things. Okay, so let's see, just make sure I've run over my notes and see if I've missed anything. Yes. So lead free, which is got silver and copper in to make it lower the melting point. Then we've got the 6040. So this is what you should be using when people say use leaded solder to make for that lower melting point, to make it easier to remove components. Use your 6040, but this 6337 is eutectic, which means it's got an instant transition between one liquid and solid. So if your soldering iron isn't totally covering the whole area, you're going to have solid lumps. But you know, once you know what it does, you'll find it a lot easier to cope with. Yeah, at the right temperature, barely smoke, works perfectly. So this is watch for the flux. So you know, if you think you're adding flux to actually help things flow better, you're not. You're actually adding more flux to cool things down because you've got things too hot. There we go. I think that's about done it. I'm just going to pause. Yeah, that's it, guys. It might have been a bit of a boring one, this one. It's just my point of view. That's all it is. But you know, there's several points of view, different ways of doing it. Like I say, theory and practice are not the same thing. And yeah, but the thing about flux, if it's too hot, you just burn it away basically, and the solder before the solder even melts. The solder flux has to be at the right temperature for it to work. It's like a chemical reaction, and so you'll find that you use less flux if you keep the temperatures down. Although I mean, what I tend to do, did I mention it, is I get a temperature gauge of my meter and actually measure the tip temperature and compare it with the actual the heater temperature, and I work on that difference. Oh well, I failed to keep it under 1 hour, so yeah. Well, you all know. I'm sure you all use that fast forward button. Catch you later, guys.